Every living biological system spontaneously emits ultra-low intensity photons. This continuous emission of light, known as biophotons, is observable across a wide spectrum, ranging from visible light all the way up to the ultraviolet range. For decades, the prevailing explanation for this phenomenon has been the biochemical theory. This model assumes that these photons are simply random metabolic waste, the chaotic byproduct of chemically induced optical transitions, specifically oxidative radical reactions occurring constantly within the cells. Experimental measurements challenge that assumption. When researchers examine the spectral distribution of these biophotons, they do not see the jagged peaks associated with specific chemical reactions. Instead, the distribution of this light is almost completely flat across the 300 to 800 nanometer range. This is a graph plotting frequency against spectral photon intensity to compare the measured light of a living system against a standard thermal equilibrium model. In thermal equilibrium, the probability of occupying phase space follows a Boltzmann distribution curve, which drops off steeply at higher frequencies. A Boltzmann distribution describes the mathematically predictable distribution of energy states among particles in a system at thermal equilibrium. The actual phase space occupation of biophotons completely ignores that steep decline. It exceeds the predicted Boltzmann distribution by a factor of 10 to the 10th power in the red spectrum and by a factor of 10 to the 40th power in the ultraviolet spectrum. To produce this specific, flat spectral distribution through purely thermal means, the biological system would require excitation temperatures thousands of degrees higher than physiological survival limits. The organism would instantly vaporize. This leaves researchers with a strictly mathematical alternative, the coherence theory. This theory proposes that biophotons originate from a coherent and possibly squeezed photon field operating within the living organism. A squeezed photon field is a quantum state of light where the uncertainty in one property, like amplitude, is reduced below the standard quantum limit at the expense of increased uncertainty in another property, like phase. Because the measured emission so drastically violates the rules of thermal equilibrium, it cannot be chaotic chemical exhaust. The data dictates that the biological system is maintaining a highly regulated, non-classical quantum state far from equilibrium. Proving that a macroscopic, complex biological system maintains a coherent quantum state requires moving beyond spectral distribution measurements. We need a rigorous mathematical diagnostic to evaluate the exact properties of the light. The primary tool for this is photocount statistics, or PCS. PCS measures the probability distribution of detecting a specific number of photons in a given time interval, providing a direct mathematical window into the electromagnetic field's behavior. This is a histogram visualizing photocount statistics. A core rule of quantum optics states that a necessary condition for coherence in an ergodic stationary field is that its PCS must follow a Poissonian distribution. An ergodic stationary field is a system whose statistical properties can be deduced from a single, sufficiently long random sample, and those properties do not change over time. This distribution requirement stems directly from the strict quantum mechanical definition of coherent states as eigenstates of the annihilation operator. The annihilation operator is a mathematical operator in quantum mechanics that lowers the number of particles in a given state by exactly 1. When living biological systems are prepared in a quasi-stationary state and measured, their resulting PCS data points accurately mirror the ideal Poissonian distribution. To verify this fit and ensure the data is independent of photomultiplier hardware biases, researchers calculate the normalized factorial moments. As long as the factorial moments of all orders equal 1, the distribution is definitively Poissonian. Matching the Poissonian distribution successfully fulfills the necessary condition for quantum coherence. It confirms the biological light emission operates under strict quantum rules, separating it entirely from a purely chaotic thermal field. There is, however, a statistical loophole. Measuring any field over a sufficiently long duration can artificially smooth the collected data. If you have a chaotic field following a geometrical distribution, but you measure it over a time interval longer than its coherence time, the resulting average will mimic a Poissonian distribution. Coherence time is the duration over which a propagating electromagnetic wave maintains a predictable and stable phase relationship. To eliminate this loophole, researchers led by Fritz-Albert Popp systematically reduced the measurement time intervals down to 10 to the -5 seconds.
As the measurement interval decreased to these microsecond scales, the data's alignment with the Poissonian distribution actually improved, with normalized factorial values approaching exactly 1. Conversely, when the measurement times were extended to 10 seconds or more, the statistics began drifting toward a chaotic geometrical distribution.
The improving statistical fit at microscopic timescales strongly indicates that the Poissonian distribution governs the biological system at any instantaneous moment. It rules out the possibility of time-averaged chaos masquerading as coherence. The ultimate test for the coherence theory involves observing a biological system immediately after it has been excited by an external light source in order to measure the relaxation dynamics of its delayed luminescence. The sufficient condition for a fully coherent ergodic field is that an instantaneous Poissonian distribution during relaxation must mathematically yield a hyperbolic decay curve rather than a standard exponential decay. This diagram shows the double-chamber coincidence counting experiment, engineered to prove instantaneous interaction between independent biological samples. Chamber 1 and Chamber 2 hold separate plant or cell samples, connected by photomultipliers feeding into a central Channel 3 coincidence counter. A photon registered in Chamber 2 counts as a true coincidence only if another photon was counted in Chamber 1 within a strict preset time interval, labeled dt. By comparing the recorded coincidences against the total counts, this setup accurately isolates the probability of measuring exactly 0 photons in the preset time interval, stripped of random noise. This allows researchers to test the data against the theoretical Poissonian target. This is a logarithmic chart mapping intensity against time. The measured coincidence probability exactly tracks the theoretical Poissonian distribution throughout the entire relaxation phase. The resulting data plots as a straight descending line on a logarithmic scale, illustrating the 1/t hyperbolic relaxation function. This continuous hyperbolic alignment rigorously excludes any possibility of a geometrical distribution or a multi-exponential decay. The undeniable presence of instantaneous Poissonian behavior driving this hyperbolic relaxation serves as mathematical proof of a fully coherent field operating within the living system. Shifting the framework from theoretical physics back to biology, we have to examine how a living organism actually utilizes this proven coherent photon field. Inside the highly optically dense medium of a single cell, over 100,000 specific metabolic reactions occur every single second. Every single one of these reactions requires exact activation energy from the surrounding electromagnetic bath to form a transition state complex before it can decay into stable chemical products. A transition state complex is a highly unstable, high-energy molecular configuration that exists momentarily during a chemical reaction. In terms of pure efficiency, a single directed photon is capable of triggering 1 billion reactions per second, provided it delivers the exact momentum and energy to the right place at the precise nanosecond. To coordinate this, the system relies on physical principles, like Dieck's theory of subradiance and superradiance. This theory explains how large wavelength electromagnetic waves interact collectively with the microscopic antenna systems of the cell, storing and releasing energy as a unified network rather than as isolated molecules. The coherent field is therefore not a biochemical byproduct. It functions as an optical dirigent, a highly flexible probability field of electromagnetic waves, acting as a master conductor, perfectly regulating the timing and execution of cellular metabolism. If this phase information regulates cell growth and differentiation, there must be a measurable nonlinear relationship between biophoton emission and the physical density of the cells. This diagram shows the optimization principle of healthy tissue. Normal cells, seen on the left, maximize constructive interference internally, connecting every molecule to the network, while maintaining perfect destructive interference externally to minimize signal loss. Destructive interference occurs when two waves combine such that their peaks and troughs cancel each other out, resulting in a reduced or zero overall amplitude. Measuring delayed luminescence against cell density reveals a stark contrast. In healthy tissue, luminescence aligns perfectly with the hyperbolic relaxation curve, indicating synchronized coherence. But when plotting malignant tumor cells, the curve sharply deviates. As tumor density increases, the data becomes entirely erratic and unpredictable. This represents a mechanical failure of the optical system. the tumor tissue has critically lost its capacity for destructive interference. Without it, the tissue cannot dampen external noise, effectively destroying its optical signal-to-noise ratio. Consequently, without the ability to maintain constructive internal interference, the tumor cells cannot share phase information. The result is a total collapse of intra- and intercellular communication. Light in biological systems serves as the foundational infrastructure of living matter. Pathologies like cancer correlate directly with a critical loss of coherence, a complete breakdown of the organism's macroscopic quantum architecture.